So in the second half of this, I wanted to apply ideas from the first half to transaminase theory specifically. So transaminase is a three-dimensional quantum field theory. So it's going to be defined on a smooth three-manifold M. The fields are connections on a principal G bundle. On M, which I will just take to be a trivial bundle. And if G is simply connected, then the only choice you have is the trivial bundle. So locally, I could also describe these as sections of one forms on M tensored with the algebra of my group. Now, the action locally gets written in terms of the algebra valued one form, and it's going to have the same problems as that action from quantum mechanics that had a nice local definition in terms of theta, but really wanted to be defined in terms of omega. So the action is an integral over M trace AdA plus 2/3 A cubed with some a priori undetermined coefficient out front. One would like this to be gauge invariant. So ultimately, the space of fields, more accurately, is not connections on a principal G bundle, but it's connections up the gauge transformation. If we ask this to be gauge invariant, just to recall what that means, so the gauge group is maps from the three manifold into G. G. It acts on connections inhomogeneously and once. S of the gauge transform connection to be S of A. And that turns out to be almost true up to some global ambiguity. So to summarize, the best way to describe the global issue is to notice that the gauge group is not necessarily connected. So maps from R3 manifold into the group may have different topological types. For the gauge transformations that can be continuously connected to the identity, gauge invariance is true on the nodes. So for a gauge transformation that's that's connected to the identity, the action is honestly invariant. Just compute and check.
Sorry, you mean with values in R mod pi, or
no? I actually mean, so the thing we want. Sorry. So the gauge invariance that we seek is mod 2 pi because the action is only ever defined mod 2 pi. For gauge transformations that are connected to the identity, you get invariance on the nodes.
Oh, without mod 2 pi.
Yes. For the rest of them, there is a shift. So in general, there's a winding number, and so S of the gauge transformed connection is S of A plus 2 pi k times an integer. And when I say 2 pi k times an integer, that involves a normalization of this thing I called the trace, which I'm going to normalize precisely so that this thing ends up being an integer.
So the action, the trace splits into two paths, one coming from ADA and the other from A to the third. Would the statement be true for each of those parts individually?
No.
No.
You don't get gauge invariance.
Yeah.
You don't even get this for the two individuals. Right, so trace is normalized such that it is an integer, and then gauge invariance requires k to be an integer. And so one ends up with the famous quantization of the level in Chern-Simons theory. Now, there's another way to think about this, which is often useful and analogous to what we did for quantum mechanics. We can define the action using the equivalent of the symplectic form. We can choose some form manifold. whose boundary is M, and extend the connection. Rather than calling it A locally, say extend the connection. The G bundle and the connection. W. And then, in terms of W, define the action as the integral of the second Chern class of this bundle, where F is the curvature. So this is initially how Chern-Simons functionals appeared. This Chern-Simons 3 form is precisely engineered so that D of it is F wedge F. So
Is there a reason for not writing F squared?
Sorry, to be consistent with the rest of
Right.
my lack of wedges. So D of trace ABA plus 2/3 A cubed is F squared, working on the 4 manifold. And so this will restrict on the boundary to that action. On the other hand, we need to make sure that everything is independent of the choice of 4 manifold. So independence of W requires the integral of F squared on an arbitrary closed 4 manifold, W closed, to be 2 pi times an integer, and that again imposes the same quantization on K. So we recovered that same condition. Okay. The classical equations of motion never done this, you can check. They simply say that the connection is flat. So classical solutions to Chern-Simons theory are flat connections on the 3 manifold M. And the next step is to proceed to find the Hilbert space. Any questions on that? Okay. So there are a few different ways to describe the Hilbert space. What I would like to do is to reduce the problem of finding the Hilbert space in Chern-Simons theory to quantum mechanics. And the statement I want to get is that Chern-Simons theory on a 3 manifold that has the form sigma times R is equivalent to quantum mechanics on R with target y equal to the space of flat G connections on sigma. Modulo gauge transformations. The part of this, the only part of this that should be surprising is the word flat. So, in general, if you have a quantum field theory on some compact space times R, you can trivially rewrite that theory as quantum mechanics, whose target is field configurations on sigma. And so, without knowing anything else in Chern-Simons, I could have said, well, the theory is equivalent to quantum mechanics, whose target is G connections on sigma. The really nice thing is that one can actually restrict to flat connections. And then this ends up being a finite dimensional space that, in fact, a finite dimensional Kähler manifold that gets geometrically quantized.
You mean irreducible flat
No?
because the top dimensional cell of the character variety is part of the manifold that is irreducible. So you want Y to be a manifold, right?
No, this is all okay. And especially in cases when one starts taking a complex gauge groups like SL2C, it's actually important to have them all.
But that's that you said Kähler manifold. That's what triggered that.
Right.
So it's a Kähler variety.
You're worried about the word manifold. Yeah, right. Stack. Okay, so why can I restrict to flat things? Let's actually do the computation. So when I work in local coordinates, what I think of here's sigma, here's the R direction, and I'll call the R direction x0 or time, and I'll use x1 and x2 as coordinates along sigma. Then the connection locally takes the form a0 dx0 plus a1 dx1 plus a2 dx2. And then one can check that the integral over sigma times r of the Chern-Simons form can be rewritten after an integration by parts as a0 times the curvature in the 1, 2 directions plus a2 d0 a1 dx1 dx2 dx0 dx1 dx2. So the trick here is to realize that there's a single derivative in the action, and that the that the derivative can always be moved away from a0. So in this form of the action, a0 doesn't have any derivatives, and it can be integrated out of the path integral the same way that we did it in the morning when we integrated out p and found that time evolution was trivial. So if we write down the path integral, it's an integral over the three components of the connection. And since a0 sits by itself, we'll integrate that out and introduce a delta function. What is a delta function of? It's a delta function forcing the curvature along the surface sigma in the 1, 2 directions to be 0. And then there's something left over. So here we have e to the 2ik integral over sigma times r trace a2 d0 a1. Times some dx's. So the presence of this delta function is precisely why one can restrict to flat connections. And moreover, one reads off from this an effective quantum mechanics action. So, so the leftover action we write it slightly differently, maybe more suggestively, is 2k integral over time times the integral over space right in the same form at the moment. Could even turn d0 into a dot, so it looks very similar to stuff we had this morning.
So I'm a little bit confused. So F12 was the 1, 2 component of the curvature.
Yes.
So if that's 0, that the whole connection has to stop.
Sure. So
Oh, I
there's
see. Oh, correct. I see. Yeah. I see.
There's an extra an extra ingredient that can be done, which is to gauge away the a0 component. So there's some gauge fixing that I haven't said much about yet, but to be rather careful, one should go to a particular gauge, and one way or another. Here I've actually integrated out a0. There's several different ways of making this argument, and they all end up in the same place. So here the only thing that's left is actually the connection along sigma, and that ends up being flat. Actually, all I want to say. There's an effective action which I want to compare to the pullback of theta form that came up in topological quantum mechanics. And in fact, when we realize that this theta is coming from a symplectic 2 form, that's the Atiyah bot form on the space of flat connections on the surface sigma. So in a more invariant way, that looks like an integral over sigma of the trace dA wedge dA, where these are differentials along the moduli space of flat connections. So we get quantum mechanics whose target is flat connections with the Atiyah bot symplectic form. And now we can identify the Hilbert space.